Let's continue working on our tick logic. Hello everyone, this is Ali Reza. Welcome to the Mentor Code Lab. In previous episode, we wrote our blackboard for our behavior tree design. In this video, we want to write a node. Now, a node class should be abstract. So we have abstract class node. Makes sense because we want to prevent users to say, I don't know, something equals to new node. The node itself is infrastructural class. Blackboard is complete. It's not abstract. We can say that some blackboard equals to new blackboard, but node is an abstract class. For this, we will have to think about a single node. Each node can have a blackboard of itself. That's the beauty of behavior tree. We have a general blackboard that is inside the behavior tree, but each node can carry his own blackboard that he will use. Now, here's a problem. We are not reading and writing NBTs for these blackboards inside the node and behavior tree. In other words, when we start the game, those blackboards will only carry some default values. In each tick, we are responsible of setting these values if we want. We'll take a look at that. If we really need to, then we have to come back and revisit the blackboard and, I don't know, write read NBT here, and then inside a node we will have two methods, read and write NBT. Inside the behavior tree, read and write NBT, and then inside our JiTickLogic class we will call the read and write behavior tree, and it will loop through nodes calling the read or write NBT, and each node will have to handle his own blackboards. Things will become confusing when I'm explaining things, but when we write the code, it will not be as confusing. The only thing is that in the blackboard, we have this map, and this map is not providing any codec. And honestly, it's just object. So I'm not sure, do we have anything like codecs.object, basic object? Oh, do we have it? If we have it, codec of object, yes, then maybe we can serialize our blackboard. However, it's a map, we need to convert it to something else, and then we will have to see that when we are doing the serialization. Anyway, I think I have a plugin for that. I'm not sure if it will work or not right now. No, I think I disabled it. Anyway, so we have to write a codec for our map, but that's a trivial thing for codecs. Let's start with a node. So as I said, each node can have its own blackboard, but the blackboard of a node should not be visible outside of that node. Keep that in mind. In behavior trees, nodes are black boxes. They have to do everything inside themselves. Nothing outside of the node should access anything inside the node. If the node needs to inform anyone else about some result or some value, the node needs to write something in the general blackboard of the behavior tree. But there are very, very, very rare conditions that I can't even imagine why you would have a node that has some get methods, for example, or set methods. Everything should happen inside the node itself. So anything you have in the node will be protected. So we have a blackboard and we call it blackboard. Then we have a protected list of nodes. This is the children. So children, and we instantiate it immediately to be a new array node. Then another protected, a single node to be parent. And now I think we are good to go. So we have a protected, a behavior tree. That is the tree we are sitting in. And that's it. So we want a constructor that accepts nothing, okay? And this will be actually an empty constructor. Now, if you want to, you can instantiate it inside here. That's okay. Public node, this will accept a blackboard. So blackboard, we call it blackboard. And here we say this dot blackboard equals blackboard. We want to be able to add a child to this node. Any node in behavior tree can have children. There is one single node that will not have parent, and that is the start node. We will talk about it in another video when we are writing our nodes, but every node will have children. Public void add children. And here we will say a node that is child, all we are doing here, we will do two things. We will say that, hey, children, add the child, but at the same time, on the child node, we have the parent, and we want to make sure that the child is already aware that this node is the parent node. Okay, let's demonstrate it. If I add a child like the no progress to this start crafting, I will call the start crafting.addChild no progress. At the same time that I'm adding it, I will set myself as the parent node of this child. That is what we are doing here. Then we will have a public void set the tree, and here we want a behavior tree, and we can say this.tree equals 3. Then we want for each node child inside our children, say that, hey, set the tree for that child. Basically, this will make our life easier. I mean, think about this situation, for example. I have the start crafting and 5 children. So if I want to create each child, assign the tree to each child, and then create the start crafting, assign the tree to start crafting, that's a tiresome code. However, I can say, hey, instantiate the start crafting node, this node, this node, this node, this node, then set these as the child of this, and finally at the end, set the tree for this, and it will automatically look at its children and say, hey, your tree is the tree that I'm in. And that actually makes sense. Okay, so that's it. Then we want a reset. So public void reset. Now remember, each node will return a success, failure, or running. But when we reset, we will say that for each node inside children, reset the children. And here we have something that we can do, but if I want to do it here, then things will become hectic. Remember, we are not resetting ourselves here because we will have a behavior tree. And normally, when we are in behavior tree, we will have a reset method in behavior tree, and that reset method on the behavior tree will reset the running node, and we will see at the logic at that time. If we still need to, then we will reset the node itself here, but I think we can avoid that. So when we are working in the behavior tree class itself, we will have an active node or a running node, whatever you call that. When that node returns success, it's the job of behavior tree to find the next thing that needs to be run. When we want to return anything, maybe we want to know what was the parent of this running node. Because of that, this is the only thing that will have an accessor. So get parent will return the parent. As I said, this is the only get method that we have in all of this, all the time. So we have a public boolean, and we call it is child of a parallel node. Now this will play its role later. If this node that we are writing and working with is a child of a top node, and that top node is a parallel node, then we want to return the parent instance of parallel node. Now we don't have that, that's okay, but this is a check. We are checking if we are a child of a parent that is parallel node, a special type of node. Finally, at the end, we have our heart of the node, public abstract, that returns a tick status, and we call it execute. Or we can call it tick or anything else. Let me go with the tick name because that makes much more sense to Minecraft guys. So this is the heart. Any class that we extend from node should have a tick method, and each tick method will return a tick status. Now this is the boilerplate of the node class. Honestly, that's it. As simple as it is, but at the same time as powerful this can become. In the next video, we will start working on our behavior tree. If you like these videos, please subscribe to the channel, hit the like button, and turn on that bell so that when I publish a new video, you will get informed. Have fun everyone. Bye.